Now you can.
Okay, thank you. Yeah, so it's a great pleasure to be back, and thanks for having me. And so I prepared something a little bit high level for like normal seminar audience. And but let me know if yeah, if you have any questions on technical details, just feel free to ask. So it's some of the work I've been doing with my fantastic master student Yopen Liao and our new postdoc Jasper. And so we're interested in some structures that are actually in very simple QFDs that even the first year grad student can calculate. The question is, can we find new structures? And today I'm going to tell you with some results that has tied to fundamental principles, but also come with some implications from logic. So normally when we compute the RG equations, we just compute radar function plot as a function of energy scales. We don't think about too much about structures, but they are beautiful theorems in special conformal field series that has very general results on relating the coefficients between UV and IR. So these are so-called 2D C theorems or the 4D A theorems for conformal field theory. So the basic question I want to ask is that do we have some analogy of this very definite control of IR between low and ING theory for more generic on the field theory? And so this is toward with the R toward homological application. And so the platform we're going to apply to is the so-called standard model effective field theory. So the idea is that if we say the energy for our collector experiment, maybe it's below the scale of new physics, say based on new particle lambda, and you want to parameterize the deviation from the standard model background, so like this slash line, in a very systematic way. And the most model-dependent way you can do that is to just write down effective field theory, order by order according to the scale lambda. And you start to have these high-dimensional operators comprised of standard model fields consistent with standard model symmetry. And you have operators from dimension 5, 6, 7, so on and so forth. And it's a very systematic and consistent framework. And I think historically, people in the experimental side, they try to put fudge factors for each obstacles. And it's actually not very consistent because these may not be compatible with gauge invariance. So even experimentalists now, they begin to adopt this framework for maps. So for instance, for the CMS group, they have the constraints. They have actually a quite large survey of these Wilson coefficients. So for instance, here is like the Wilson coefficients involved platform. And the typical energy scale for this high-dimensional operator is about 1 TeV for most of the HC results. And so the typical method for effective field theory is that we integrate out a new particle at the energy scale of lambda. This is by the so-called EFT matching. And once you go below the scale, say the LGC energy, you need to perform normalization. And it's relevant for two possible scenarios is that first, the new physics scale lambda may be much higher than the experimental scale. Another scenario is relevant is that when you compare experiments at two different energy scales, such as LGC or B or K may some factors. And in that case, you may even need to switch to a different effective field theory framework. And so that's a reason why people put a lot of effort into completing the normalization group equations for the standard model EFT for SMAPT. So these are the famous results for dimension 6 by the San Diego group. And there's been a lot of work for completing this at the dimension 8 levels. So it's not, even though we know a lot of pieces for dimension 8, but it's still not completed yet. And you can ask like, why this is so difficult? And the reason is that by going this model-dependent framework, you pay a huge price for the complexity. So we organize the operator in terms of the dimension. So the only two operators, the usual one-grid operators at dimension 5. And for most of the LGC processes, we're interested in dimension 6. So that's about 100 operators. And for the typical next order in the EFT expansion, let's go more toward dimension A, where here you have about 1,000 operators. And this is even before you count the flavor structures for these high dimension operators. So this definitely call for new structures for SMAP for EFTs in general. And maybe things okay, maybe there's just nothing interesting. But it turned out that by this explicit calculation, there are very interesting results found by Alonso, Jenkins, and Mandelhart that even for the dimension 6 level, the leading result for the EFT expansion, that operator J can renormalize into operator I. And we have a so-called non-summation matrix. And so for this matrix, we can classify them in terms of different class of operators. So this operator renormalize into operators here. And the surprise is that even though many of them have non-trivial Feynman diagrams, but a lot of them turn out to be cancel or zero. So all this entire green area, all the results they are zero after a non-trivial cancellation. And so yeah, many years ago, Cliff and I explained this by Thirsty and Unitarity. So this gives us hope that yeah, maybe something interesting is going on for this normalization structure. So yeah, maybe there's something interesting. And for today's talk, the new results will be primarily for dimension A level. So I should explain that even though we have some Q stories for dimension 6 as well, but I should explain why chronologically it's relevant to talk about dimension A operators and also go beyond shear level. So there are basically two possibilities that dimension A for running will be important. The first scenario is, as I mentioned before, if you have a large scale separation, maybe it's coming from experimental data from different size, or if your certain observables, the cutoff has been pushed very high. So for instance, for low energy procedure measurement like K meson mixing or the mu to E conversion, the cutoff is like 100 TeV or much higher. And so in that case, RG running is important. And the second type of scenario where we're interested in dimension A or this the RG running is that certain observables, the leading effects start with some dimension A. So for instance, the light by light scattering, this corresponds to after the force operator, this leading effect is at dimension A level. Or when you study Higgs decay in the UV complete model, the Higgs to gamma gamma or to blue, these are the loop level process. So in that case, for the corresponding operator, these loop induced operators can be contributed by the tree level operators from other sources. And that's why you also want to consider RG. And the last thing is that for when we compute the amplitudes, usually dimension 6 is the leading effect. But when you compute the cross section, sometimes the heuristic doesn't interfere with the standard model. And for the same zeros I mentioned before. So in that case, the cross section, the leading effect start with a pair of dimension 6, which has the same EFT power counting as the interference between standard model and dimension 8. So all these are the scenarios where dimension A or the runnings can be relevant for geometrical interest. Okay, so now just to give you a concrete example, so let's consider the structure in the Higgs sector. So we have the standard model part, which is basically the lambda 5 term. The dimension 6 part, we have these three different operators for Higgs. The first two has the 4 Higgs field, the last one just 5 to a 6 potential. And for the dimension 8 part, let me focus on the three operators that involve 4 Higgs. So they have different contractions for the favor or the renormalization. So when you can easily compute the RG evolution here, because these are dimension 8, so 1 over lambda to the 4th. So there are two types of contribution. One is coming from the standard model lambda 5 for dimension last coupling interfere with dimension 8. So this is the first result in the first time. But you can also have a pair of dimension 6 operator that gives you 1 over lambda to the 4th. And you can compute the RG versions one by one for each of them. And here I'm using a generic SUN group just to see the structure more manifestly. But the bottom line is that from these simple operators, you don't see very simple structures. At least not very obviously. But now let's rearrange this operator a little bit, and we'll rearrange this according to the process you can measure by the forward limit. So by forward limit, I mean the initial and final states are the same, where the usual minus T variable goes to 0. So now I'm just doing a combination of the same the operators I have. I have C2, C1 plus C2, C2 plus C1 plus C3. So the first line corresponds to standard model times function A. You still don't have very clear structure. But something interesting going on for the second line coming from the pair of dimension 6. So you can see that even though you have now several coefficients, but they all complete into squares. And not only they complete into squares, the prefactor is always negative. So it's always negative from here. And yeah, I have a generic SUN group, so you can see that it's true for any gauge group SUN. So that's something interesting going on. And for aspirants in the audience, you can see that I'm arranging operators one-to-one correspond to the forward limit. So it has to do with the so-called positivity bounds, which is actually the, yeah.
Sorry, just to understand the notation. It's this is like the beta function for the coefficient.
Correct.
So this multiplies a log.
Multiplies the log. No, it's a coefficient of the log.
Yeah, exactly. It's the coefficient of the log. Okay, yeah. I just wanted to
yeah.
make sure I understand.
And suppress the factor of 16 plus
Yeah.
square. Okay, so let me give a quick line review of passivity bounds, although I think you probably heard a lot of this in the previous seminars. So that's actually a motivation for this work. So the question is like, given this large complexity, how should we constrain effective field theory? And a very nice result from literature is the so-called positivity bounds. So the idea is very simple, that you just assume very basic properties about UV and see if you can get anything interesting for the IR. So the simple properties that we assume are energicity, unitarity, and causality. And we consider a simple process with two-tube scattering where the T channel, Mendel's and T goes to 0. And this is so-called forward limit. So if you consider a simple strip symmetric scalar theory, the leading interaction goes like d phi to the 4th. So you have this 4-point amplitude in the IR. And so the statement about energicity is that we only have branch cuts when we have particle production. So this happens if you go beyond the region of EFT that we can produce new particle. So that's why these branch cuts start with S greater than lambda squared, or for negative S, which corresponds to the U channel scattering, you also has a branch cut. And the discontinuity for this branch cut corresponds to the AA dagger according to the optical zero. So when we go to a forward limit, the discontinuity is proportional to the cross section, where this n is any intermediate particle in between. So now we can play the game from Cauchy theorem that we close the contour using this kernel to pick up this CA coefficient in the forward limit. And now we can blow up this red contour, which will give you this pick up the contribution in the UV by this discontinuity plus a potential boundary return at infinity. But from causality, because we know that the amplitude cannot go too fast, and therefore this contribution from infinity is cancelled, and therefore this red contour equal to the blue contour. But we also know that this discontinuity.
I don't understand.
Yeah.
So on the previous page, you showed us a result, and you say that result can now that was entirely EFT.
Yeah.
Purely EFT, and there was certain positivity that we could see.
Yeah.
Visible. But here the positivity depends on the assumption on the underlying theory.
Excellent, exactly, yes.
So, but then, how did that EFT know that this underlying theory has this property?
Yes, that's precisely, yes, that's a difference. So in the previous example, that's a purely statement in EFT. It doesn't know anything about UV.
Right.
And it's in contrast with this statement about passivity, which rely on simple, but certain assumptions about UV, yes.
But wasn't the
But
previous
this-
slide positivity of the change in the coefficient, not the coefficient? It was C8 dot equals
It's true, but
minus
yeah,
something
there's
squared.
still the mismatch in the, where you still assume different things. One only.
Yeah,
assume-
I agree with
yeah,
that statement, but I'm just saying like, these are the different bounds, right? The other one was like.
They're
positive
just
beta
different statements, they're not the same
Okay,
statement,
great.
so that's why. Yeah, different statements coming from different assumptions, so I'm not, yeah, I want to cross-examine between these results.
I mean, analyticity is also true for the EFT. You also have like the upper plane to be,
What's that?
the analyticity is also true in the EFT.
Well, but
So you can also
the-
create arcs inside the EFT and
In the
compare
previous
the
slide,
function.
the EFT doesn't know anything about the sign of C8. Right?
So far, just view them as two separate results.
Oh, okay.
That's-
It
we'll come
knew
back
nothing
to,
about the change,
yeah,
the beta function.
we'll come back to interplay,
But anyway, there's a result without this assumption entirely in the EFT,
yeah.
so the question is. Anyway, you're
Yeah,
gonna answer that.
yeah.
Good.
Okay, and it's enticing this result because at least we have some non-trivial constraint for the EFT coefficient. Because this coefficient corresponds to this contour interval, which must be positive by unitarity. And so this, and that would be great for this math, because experimentally, normally you measure some contour in this parameter space. So I stole this part from Grant and Nick. So the Grant and Nick, they pioneered this program, say if we can apply positivity bounds for SMAP, at least we can have some theoretical prior to where we expect this coefficient will be. So that would be nice. And so for instance, they derive this result based on the same technology I reviewed earlier, the previous slide. Now exactly the same combination appear, the beta function I showed. But instead of showing the change, the beta function, now these all have to be positive according to this positivity statement. But the question is, this is phonology, so don't get to assume what you have. And importantly, the branch cuts appear when you have particle reduction. But the EFT, because you have light particles, so you also have particle reduction. So the branch cut doesn't stop at the EFT cutoff, but you go all the way here. And that's why you need to modify the previous positivity bounds. And that's been put forward by quite a few recent works, including like the work by Julia. And so one approach is to understand how do these positivity bounds modify when you have this branch cut structure, this change in the infinity structure in the IR. So that's one way to approach this problem. A different question you can ask is that this branch cut come hand in hand with the fact that the Wilson coefficients, they're really never a constant. Because once you have a branch cut, you have log, and then the Wilson coefficient will run. And as I said before, that for this process, they have two possible contributions. And if you check the result from chiral perturbation theory, these logs are not measurable. So you do need to take into account.
So when you say something is positive, at what scale is that?
Yeah, that's the obvious question.
Like, well,
So you have to do this type of, you have to pick a scale. So
so
of
what's
course,
the range in their analysis? What range would you give this scale?
so in simple words, they're bounding the amplitudes, not the Wilson coefficient.
Right.
And amplitude is always invariant under the choice of mu. So in practice, they say pick mu to be equal to lambda, the cutoff, and they're constraining. So the result they have will be integrated as like the bound for the coefficient at this scale. But of course, they're constraining amplitudes which are invariant under the choice of mu.
It's the size of the arc. The arc in the IR, if you take it larger, then you probably have like larger energies, and that controls the running.
And so when you say in the last bullet point, like coefficients run, you're running from the what to what? Just to clarify.
So good. So I'm not trying to do what you've been doing already, trying to study how this arc will modify the positivity bound. The alternative strategy we want to ask is that forget about positivity bounds. And just say if suppose you have a coefficient that's positive and matching scale, does algae want to bring you to the more positive side or can RG running bring you to the negative part? So it's not the same direction that I've been pushing, but it's a complementary question. Or in other words, imagine if some people are trying to tell the experimentalist to measure this one and conform with positivity bounds. But the question is whether just with the low energy Lubin effect itself, can this validate the naive positivity?
I imagine a scale of new physics, and then you run it down to like whatever the collision is at.
So if we see a validation of these tree-level positivity bounds, is that saying that UV series is non-unitary, or just mean that it's more subtle, we can't take these bounds literally?
On a practical level, like the difference would be a log, which is a loop effect.
Yes,
So, and it's also commensurate with like the finite piece of the loop.
I'll give you an example. Yeah, so usually, yeah, that's kind of worse. People say that, yeah, it's a little bit fast, or expect this to be small.
Right.
But there are examples you can find that it's actually not.
Yeah, no, I'm not making a comment about the size. I'm just saying, making sure I understand, like, it's the loop effect, right?
Yes.
You can call it RG, but it's really,
It's,
Okay.
yes, indeed. It's the IR will be flat.
including the finite piece, like the finite piece would also.
No, I'm only thinking about RG, which is the log piece.
But then the finite piece would be the same size.
The finite piece, depending what you want, because the finite piece, it's the loop amplitude, so I don't know if you want to call that the coefficient. Yeah, it's you're constraining the amplitude if you use the correct positivity, so you're not. The difference between the log and the finite piece, they all just come together as amplitude, which is the object you want to constrain. Okay, good. So just to give you more concrete data. So these are the same three combination, same three operators I showed before. And here, let me just focus on the case where I have a pair of dimension 6 operators. And instead of just having the Higgs factor, now let's have like fermions, gauge bosons, all possible intermediate particles. And you can check that very non-trivially, all these cases, they have the same property that it's always overall negative times some sum of squares. So you can have like 10 different dimension 6 coefficients, but they all completed into squares. And like for the case of fermions, yeah, you need to put a minus sign for the fermions for the fermionic group. And even with non-trivial flavor structure, this average means that you're summing over the flavor structure, but it's still a positive matrix. And the same thing for the gauge boson loop that if you have FF dual, then you also need to take into the size correctly, such that it gives you the same uniform results. All right, so let's try to. So as I said, that I'm not directly. It's very much related to motivated by positivity bounds, but we'll take a different approach and just try to understand the structure in RG.
Just to make sure, like, what is not a square? So suppose I had a linear C1 times C2, I can always add and subtract.
You can always
C1 squared and C2 squared to make it a square, and then.
right, but you can have you complete a square.
Mhm.
You can have C1 plus T2 squared
Yeah.
minus C2 squared.
Okay.
So in that case, you don't have
Because
uniform sign.
it's also important the overall sign. too.
Exactly.
Okay.
So yeah. So you can always, especially for the cross terms.
Yeah. Okay.
Yeah. That's right. Right. So let's try to understand these few results from these fundamental principles. And I think for amplitude people, this is very straightforward. We're probably too trivial. That when we chase the RG, we're chasing the log mu dependence we generate in our calculation. The log is dimensionless, the function of dimensionless argument. So the log mu is compensated by some other convective invariant like S, T, or U. And we consider mass as particle such that we don't need to worry about log m squared over mu squared. But when you compute the full amplitude, it's invariant on the choice of mu, so that the mu dependence for your renormalized tree amplitude should cancel the mu dependence for your 1D amplitude. And the mu dependence of your 1D amplitude, because of this relation, 1-to-1 correspond to the log of STU. So then we're summing the log of coefficient of ST and U separately. And the coefficients correspond to the discontinuity which we can use optical server to provide it as a dagger. So in the way that this bubble give you a log, which through your 30 cuts, we can have the AA dagger integrate over internal phase space. That gives us the log, this continuity for each channel. And it's important that the mu can come from all possible channels. So we have to sum over all the kinematic part like STU. And yeah, and this is a simple case where we don't have 3-point coupling, like gauge coupling with the active operators. But of course, there will no treatment how to incorporate this in the S matrix way. All right, so as a very simple example, you can check the lambda 5-4. Okay, and each amplitude here is just a constant. So when you integrate over phase space, you'll get factors of pi, and you'll get this usual 16 pi squared loop factor. The important part I want to say is that you do need to sum over STU, which give you a factor of 3, and that's the correct answer. So if you just summing over maybe S and U channel, it's actually not the correct beta function. And the reason it's important is that now we can consider our case where we want to do RG in this unsure way, and want to consider forward scrapping. So we want to consider kinematics in this way that the final state and the initial states are the same. Imagine I have particle 1 and 2 coming in and the same particle going out. And so we need to go over this continuity for the S, T, and U. And for the U channel, I'm crossing the top line, so I get minus P2 minus P2. But for either S or U channel, these have the properties that in this particular kinematics, the initial state and the final states are the same. So I call these like forward channels in this kinematics. But this is in contrast with the T channel, where this particle is crossing with this one. This one, these two are crossing, such that my initial state become P1 minus P1, final state is P2 minus P2. Also, they don't have this forward limit that the initial and final states are not the same for the T channel. Okay, so that's analyze them in turn. So for the forward channel, you can sort of guess what's happening because using the optical server, initial and final state are the same. So you just have a positive matrix. The only subtlety you have to take here is that we're not looking at the full amplitude. We're looking at certain part of the amplitude correspond to a rounding. So we're truncating this positive matrix. So you have to make sure that the truncation is still positive. And when you have S and U channel, you get the same sign between these two terms. So the first part is straightforward. So even though when we do truncation, maybe it's not positive, but at least when you restrict to a subsector, the same sector in your amplitude, then it's still a positive matrix. So that's why if I consider inserting operators of the same mass dimension, so maybe you have 100 dimension 6 operators, but at least it's the same part of the amplitude, and therefore this truncation is positive definite. But this is in contrast with, say, if you have a standard model part like lambda 5-4 interfere with some dimension A, you don't have the same sector, and therefore it's not a positive matrix anymore. This interference term is not positive.
But you could consider it as a matrix, and then it's like positive definite, right?
Right, but it's the overall.
Yeah, it's the full
amplitude
matrix.
is-
That is.
Right. If you look at, if I just want to know the d5⁴ coefficient, I
Yeah.
wouldn't be able to tell. Or if you look at the particular coefficient, I can't tell whether it's positive or not.
Yeah, there's more constraints. Yeah.
And the second part is that now we can take the dissimilarity for the S channel and the U channel, where in each case, the energy is positive on each side. But the problem is when in the forward limit, S and U simply have a relative minus sign. So when we consider the previous truncation where all these coefficients, A0, A1, A2, they're all positive numbers. But even in that case, when I combine the S and U channel, the even part of S will be fine because it's always a plus sign between them. But the odd power will have a relative minus sign. So at least for the most sufficient condition, you can just consider the power correspond to even power of S, like the dimension A contribution, or this correspond to a loop of a pair of dimension 6 operators. So any even dimensional operator insertion will guarantee that you have the same sign between S and U. And so this is sort of the reason why like dimension A is really the primary example, is you always have this guarantee from the sign between S and U channel. But we'll see more examples for dimension 6 later. All right, so okay, so it's straightforward to ensure passivity for the forward channels that we just need to insert a pair of even dimensional operator. So this channel is a little bit more tricky. So the initial and final states are not the same. So the integral itself is just not positive. However, you can dive into the problem a little bit more carefully. So even though it's not positive definite, the kinematics is extremely special. So the total momentum of, so let's consider internal particle L1 and L2, and which have spin H1, H2, and some extra derivatives acting on these operators. And so you can use Renormalization that just by the counting the little group, that it must have this angle and square bracket to the power of 2 times spin plus any extra derivatives on these internal particles. So for instance, like for the case of fermion, you have the L slash, which is like 1 power of angle and square bracket. And for gauge boson, you have a field strength on both sides. So you will have L to 2 powers, which agree with this formula. Or if you have scalars with any derivative interaction, then you just also add extra powers to this internal fluid momentum. And we know that this is a Lorentz invariance problem. So the only momentum flow into this problem is the total momentum here, which goes to 0. It's not that we're setting the p squared to 0, but just the entire full vector goes to 0 in the forward limit, which is very special. And therefore, just by power counting, it must be proportional to this external momentum to this power. Such that then we realize that this contribution is always vanishing whenever you have any non-trivial spin, or if you have any non-zero derivatives. So then, in other words, the only case where you get a non-zero result from this channel is that you only have scalar particle without derivative, which is really the lambda phi 4 example I showed you before. So lambda phi 4, very interesting, is the only validation that you get non-trivial result on this T channel.
Is this the same analysis for the paper?
Not really, because we will consider generic kinematics. But the idea is that now for RG, you can still measure the RG by going to special kinematics.
Yeah, of course, that counterexample is in the standard. So, I mean, just the lambda phi before.
Yeah,
Just
yeah,
the
yeah,
names.
yeah.
So, you account for it, or what do you do about that?
So, yeah, so we don't have statements in that case. Yeah. This result by itself is actually, you can phrase that as a corollary that it's actually a non-normalization statement, because that means for this particular channel, there's no log for this special kinematics. And I'll give you example on this later. But now you can combine all the ingredients, and so just use our on-shell formula for RG. The run name corresponds to this continuity for all possible channels. And we use the unitarity and anticity to write as a dagger. But now, since the T channel doesn't contribute because of the Lorentz invariance, we only need to sum over S and U, and we can guarantee that it's not sign definite, as long as we insert a pair of even dimensional operator. So that would make all these coefficients positive. So overall, you get minus sign for the running. So in other words, this is like an A theorem for effective field theory, that the coefficients the running for this particular sector, inserting a pair of even dimensional operator is always sign definite. And coming back to this question, so as you can see from my proof that there are no properties being used for the UV. So this rounding is purely an IR effect. So you can have like some lattice UV completion, but it doesn't change this story. So I think Peter, what it means is that the RG rounding is negative, so it means that if you start with something positive, then it will remain to be positive. Okay. So let me make a quick comment on this set of series of papers by Chia-Hsien et al. So they're the one who made this important observation that the RG has this interesting size. But what's different is that they're really trying to push this pseudo positivity, the usual positivity. But the crucial difference is that this is really a property about infrared. So it's not about UV neutrality, etc.
Sorry, doesn't it say a little bit about UV that UV completion has to satisfy that assumption of what happens in infinity?
No, we're not doing counter integrals at all. That's
No,
why.
sorry, I mean that. So there's the IR and the EFT, and that has nothing to do with the UV. On the other hand, if I wanted to derive the same result, imagining a UV completion, I'm assuming.
Yeah.
Now the behavior, the UV at infinity.
Sure.
So then doesn't that imply that the UV completion must satisfy good behavior at infinity?
No, we're not saying the absolute value of C is positive, we're just saying that rounding.
I see.
Yeah.
Equal. Okay. I got it.
So we're saying that object has to go this way, but it could, or it may or may not be that it may stay positive or it may go negative.
So it's slightly different.
It's different.
From the.
Yeah.
Another way to recover this using contour integrals would be to just build two arcs in the IR, both of
Subtract
them.
Yeah.
And then I guess since you don't do any integral infinity, you don't need any first
Right.
R bound. So
Good,
I guess
good.
you get the same result.
The slight technical difference is that you still need to argue why the difference in this branch cut corresponds to rounding. And that's why you need to say
Okay.
that T channel discontinuity is irrelevant. And that's why I need to go over this T channel, because by this contour, you pick up the S and U because you fix T.
Okay.
So say, for example, this would have been wrong for lambda 5,4.
I see.
Because
Okay, so because the argument I saw was only for like Goldstone, so maybe you need those
Yeah.
derivatives to have
So
like
of course-
adjusted.
it doesn't
For
affect the
limit?
result because we show that any year of T contribution, that T channel will be gone.
Right.
Yeah. But yeah, it's for me that I need to fill this gap that
I
the T
see.
channel doesn't affect the RG one.
I see.
Great. And because we don't use contour integrals, so we're not bounded by first bound. And of course, this is purely protective. But the advantage that if we can go to different corners where we don't have control in non-protective approach, such as like dimension 6, and also like higher points or higher loops. And I think the technical difference, crucial part is the part answer that the T channel contribution is 0. That's important for the argument. But I want to discuss this in the more formatical setup. Like, so we have this contour mathematical equation, but how do we tell its parameter is like what kind of direction of our G that we can find? So as a great concrete example, the current perturbation series is like a golden example. So we have order P to the fourth coefficient, which is normalized by a pair of order P squared. And for this term, we can apply our theorem and you find that RG rounding is always negative. And to make connection with the standard model, imagine now you consider the yin and coupling, which is weak in this context. So you have a self-normalization to the same order P to the 4 coefficient, depending on proportional to the alpha in yin and. But in the pharmacological case, the alpha is small, like 0.1%. And therefore, this contribution is actually very small, like order P to 6 compared to the other contribution. So even though we don't have the full control of RG for the current perturbation theory, but pharmacologically it's dominated by this particular term, which governs this particular direction of the rounding. And in other words, according to this paper by Shen and Howard Georgi, you should think about this as that because this is a strongly coupled theory. So the loop from this the chiral loop from the chiral perturbation theory is relatively not surprised because it's a strongly coupled theory.
You had an example that the sign wasn't preserved so that you passed to zero.
I'll give you
What's
that.
special? What's
I'll give you that.
Okay.
So now apply to the standard model case. So one to ask like when the possibility will be preserved or violated. So it will be preserved if this term is dominating. And just to make an analogy with the chiral perturbation theory case, that means the higher dimensional sector, these operators are more strongly coupled than standard model. In the sense that if the standard model coupling is relatively weak, then this term is suppressed by this weakly coupled standard model. And therefore, the RG is dominated by the first term, which go in this way. So this is the direction of RG if the new physics is strongly coupled. But if it's a weakly coupled model, we don't really have the control of sign. It can go like either way. It may be still negative, but stay positive, or it's negative in a way that would literally cross the zero. And we want to give a simple example that the passivity can be validated from RG. So let's consider the Higgs doublet, but let me turn off all the gauge couplings and the symmetry breaking. So I have a normal singlet with heavy mass m, a Higgs doublet with a small mass m squared. And we turn on the usual lambda phi 4 potential that we have a lambda for the Higgs and the G for this singlet and the pair of Higgs. And we have just the EFT, the Higgs factor EFT that I showed before. So when you integrate out the singlet S, it has to have this the flavor structure among the Higgs. And therefore, two of the Wilson coefficients at this one loop latching, there happen to be zero. And so that means in terms of this tree level passivity, it's already at the boundary of this EFT region. And now, so this is for the matching, so it's in the UV. So now we turn on the RG running in the IR. So starting from this matching condition with this value proportional to G squared, you have two contributions. One is the lambda phi 4 interfere with dimension A. So this is of the scale lambda times G squared. You could have the other contribution coming from dimension 6 squared. This will be order G per force. So in the case, imagine the standard model coupling is stronger than the new physics in this case, then this is the term that dominates RG. And because C is positive and the lambda phi 4 potential is positive, and therefore RG, these are all positive. And because we were already sitting at the boundary at the UV, so all the RG rounding is positive. So it means that if you go to IR, it flows to the negative side. So this is a model where it validates the tree level passivity. And of course, if you do the full analysis carefully with the loop, I don't expect any violation, but just that if you take this passivity bound naively, you'll find that there are cases where you can simply validate this passivity by running in the IR.
So this one way to say it is if you actually had included the loops in your positivity bound,
Yeah,
there is no harm.
the bound should be like something like this, that encode this. Yeah, so the boundary, there's really never sharp boundary. That's the lesson. Which is consistent with what other people's found. Right, so I can give a few Q extensions. Because we're not using counter integrals, so we can discuss dimension 6 as well. So remember the problem for dimension 6 is that you have cancellation between S and U channel. But you can simply forbid this by some structure in your theory. So for instance, for the that one-way operator, we have the fermion side bar, which forbids the S and U channel loss. So in that case, only have one channel, and you can still have this sign definite rounding because of the fermionic structure. Which, yeah, so this is already interesting result for dimension 6. And the previous statement about T channel, will vanish in the EFT, can also give you another normalization theorem. So essentially what we try to do is that we try to measure the Wilson coefficient in the forward limit. But if this very special kinetic channel, is the only channel in your problem, then what it means is that if you can measure the Wilson coefficient in this way, we just prove that this contribution is zero, therefore the rounding should be zero. So let me give you two examples. So in this example, we consider the RG rounding contribution to this operator by lambda 5 term. So through this type of diagram with these two being the gauge boson, it's vanishing in the forward limit. So therefore you don't get interesting result. You simply set 0 equal to 0. But if you consider this like a dipole of the current type of operator, the fermion line because of this gamma mu is not 0 in this very special kinetics. But then we simply prove that this contribution will be 0 because there nothing, no structures you can have when you have derivatives, and therefore you can check that the result is indeed 0. And yeah, even though this is very perturbative compared to the usual passivity program, but nice thing is that now we can go to higher points or even and also higher loops. So we can consider this typical example where we have a sunset type of diagram. Indeed, the RG also has some fixed sign. And we can also consider examples like this 6-point example, where you also have similar properties for these signs for the RG.
That's something you prove it by example.
It's more by example that we construct this example such that you only have this attribution for the RG.
But
yeah,
you think there's a chance that let's see the previous examples where your contributions is 1 mean, but then 2, 3, and so
yeah.
I think there might be a way of proving the sign stays the same.
We don't know because in that case the beta function is now a function of dimensionless coupling, and like gauge coupling, lambda 5, etc. And yeah, that's more complicated. So you have to, yeah, we don't know. There are probably pieces you can still leverage, like this kind of three particle cuts. If you have a piece that corresponds to these three particle cuts, and that's why we construct this example. But overall, yeah, once you add all possible contributions, yeah, we don't know.
Do you think it, I mean, maybe there's a weird question if you don't know, but do you think it might come out
I see my
Same
about
sign.
that.
the same sign for
Maybe not as,
correction?
probably not as strong as the 1-year result, but there are definitely small corners that you still have fixed sign.
Yeah, makes sense.
Okay, so there are some rights. So yeah, this standard model EFT has rise into a popular scenario for research of physics. But the price you pay is that you really have a huge complexity when you go to higher orders. And passivity bound is something that will be in principle be great, but this loop correction is actually something important you have to examine. And so we prove this A theorem for the EFT governing the bonding of the Wilson coefficients. And I think from actually what's important is that the strong coupling is the scenario where this A theorem will be more effective, will dominate the actual rounding. And I also gave you a two example that every coupling actually flip the sign in the IR. So I think for futures, there are definitely a lot of things you can explore. And I think the important part is that what happens if you consider qubit operators? Like the simple one would be gauge coupling. But in terms of EFT, you have FQ, RQ, or this have some type of coupling. And in that case, you may have higher divergence that spoil the passivity. And this is also related to like weak gravity conjecture, where people consider the rounding due to Einstein Hilbert term, which also has some qubit coupling. And so far, this sign definite property I mentioned are the beta function that are just purely numbers, doesn't depend on the coupling. But especially when you go to higher orders, all these beta function will have correction from small like alpha s or lambda. And their simple example, even one do that, you can see their interesting positivity, but yeah, we still need to study this more generally. And so the talk I showed you this sign definite property for the running, but in principle, you can also try to constrain the sign from matching. So in that case, you need inputs from UV and see whether you get some interesting sign, also based on similar character ideas. And I think some people also like to try this positivity from content information perspective, in the sense that RG is like integrating out degrees of freedom. So what does degree of freedom mean in terms of EFT? And yeah, hopefully there'll be some connection to this RG running. So yeah, so I showed you there's a broad spectrum on EFT, and of course only covering a very tiny corner, SNAP and ion. But maybe it'll be something interesting for all the EFTs as well, like black hole rotation waves. There could be something fun there as well. So there are more things for us to discover. So thank you.
Thank you again.